Bitcoin and smart contracts. So, Bitcoin, introduced in 2009 by Satoshi Nakamoto, surprisingly does support smart contracts. It has a so-called script language, that's a stack-based language, which is not Turing complete, so it doesn't allow for any loops or any sophisticated programs, but it does enable smart contracts. So you do have if and else statements, as we will see in the following. So Ethereum, on the other hand, has a quasi-Turing complete smart contract language, which we will discuss later. And in a sense, script or Bitcoin is a fork, so the Litecoin is a fork of Bitcoin and does support script just like Bitcoin does. And so does Litecoin and Dogecoin as well. Now, according to the inventor of smart contracts, Nick Szabo, so a smart contract is a computerized transaction that executes the terms of a contract. What's interesting here is that there are some terms, and these terms are actually defined in code. So people could say code is a law in smart contracts. The general objectives are to satisfy common contractual conditions, such as payment terms, liens, confidentiality, and even enforcement, minimize exceptions, both malicious and accidental, and minimize the need for trusted intermediaries. I think this is in general the core concept of permissionless blockchains, which is to minimize the need for any intermediaries that we have to trust. But what's also interesting here is that there's even the enforcement of contracts that could be done on a blockchain or within a smart contract. Related economic goals include lowering fraud loss, arbitrations, and enforcement costs, and other transaction costs. So obviously there's the need or the desire to lower costs in general when related to fraud or fights between multiple entities. So a smart contract per se is basically just some piece of code. This piece of code is executed by all participants that participate in this particular smart contract. And there should be global consensus over this execution, or at least the participating in the smart contract should all have the same opinion about this execution. So there's some form of consensus. Ideally, we have an automated verification and enforcement of these contracts because we don't want to have another third party that intervenes and might need to enforce the contracts. So a contract can define whatever contractual obligations, but it also should enable an entity A to send funds to an entity from an entity A to an entity B. So this is something that a contract should allow. So now, how do Bitcoin smart contracts look like? So let's take the simple example here of a contract that we can write in prose. So Alice will reveal to Bob a value x such that the SHA-256 hash of this value x equals to a hexadecimal value, which could be here, for example, start with 1b. So if Alice will reveal such a value, then in exchange Bob will pay $10. Right? So we could write this down, and we can also specify if Alice does not reveal by July 1st, 32, then she will pay a penalty of $1 per day that she's late, up to $100. So this is quite a traditional contract. We could now sign this, right? You can sign this here with your signature, and now if Bob doesn't follow up or Alice doesn't follow up, then either of them could go to court or seek some other remediation. Ideally, we don't want to go to any third party, so ideally we want to write down this contract in code. So we have to now convert this to some language that can be compiled to some kind of an assembly or a VM language that can be interpreted by machines. And this brings us to the fundamental differences between smart contracts and traditional contracts. So in traditional contracts, we have we specify the contract within the natural language. So like this is just, for example, English, right, as we have just seen. So this can be English. And we do have the smart contract, which is in code. So this can be, for example, in script. There are other languages such as Solidity. And these basically compile towards then some kind of a bytecode or some form of assembly that can be interpreted. So the identity and the consensus is guaranteed in the traditional sense in written signatures that are easy to manipulate, while in the smart contract world, it's digital signatures which are quite hard to falsify. So the dispute resolution, we resort to judges in the traditional world, while on the smart contract layer we have this decentralized platform itself that should account for the dispute, right? It should account for the cases where the two entities engaging in the smart contract don't agree, or the n entities engaging don't agree. So what's interesting is we don't have a nullification of a contract on the blockchain. So technically this could be maybe included, or I mean there might be some ways to, for example, on Ethereum you could destroy a contract. However, if somebody has the ability to destroy a contract, then he could just do so at any point in time if it pleases him or her, and then it's kind of part of the contract. So there's no such thing as a true nullification that would say this contract is invalid or this contract has a bug, therefore it needs to be removed. While judges can nullify contracts, payments can be legally enforced. Like this is orthogonal basically to the contract itself, while in smart contracts that's really built in, right? So the smart contract is both a legal system as well as a payment or a value transfer system. And same goes for escrows. So typically in the real world we have a trusted third party that does the escrows, while the escrows are built in the smart contract. So if we look now at Bitcoin script, we have here transaction 1, and here we have another transaction 2. And we can see that this output here pays to another input of this transaction, right? So, and we can see here that the terms basically of the input here, yeah, these are the signature and the public key, right? So this is this part of the transaction, while the second part, so this part here, is a language, is a script, right? So we have opdup, ophash 160. So opdup duplicates some value on the stack. Ophash 60 hashes a value on the stack. Then there's a constant, so the pub key hash is a constant that's pushed on the stack. So this is a program, right? This kind of a smart contract that's being evaluated, and if this evolves to true, so if the Bitcoin script interpretation engine evolves this to true, then this transaction, this new transaction TX2 here, this one is valid, and it can be basically it means that these two outputs are then also valid, right? I mean, you can basically produce this new transaction, or let the blockchain mine this new transaction. Okay. So yeah, just a small recap. Output addresses are scripts, input addresses are scripts as well, and you match them together and you evaluate them in Bitcoin. It's kind of an evaluation of a smart contract. So the Bitcoin scripting language supports 256 opcodes in total, of which 15 are disabled due to security reasons, and 75 are reserved. It's the security reasons are basically that certain opcodes might take too much time, so we want to avoid dealing of service attacks on the whole network, right? But what the Bitcoin script does support is, for example, if and then statements, simple arithmetic, plus minus division, data handling, crypto hashes. So, for example, the SHA-256 that we saw earlier. That's supported by Bitcoin script. Importantly, we can verify signatures, right? But there's no encryption, right? There's no encryption in this scripting language. So the design goals of Bitcoin script were simply to be simple and compact, stack-based, not Turing complete, but the execution time, memory bound. The execution time in the memory is bound by program size. So this means the bigger the program, the more expensive it should be, right? And this is exactly what you have in Bitcoin. If you produce a bigger transaction in terms of bytes, then you pay higher fees. That's not the case in Ethereum, as we'll see in a later lecture. But that's quite interesting that the program size is really an indicator of how expensive a program or Bitcoin transaction will be. So obviously, what would Turing say to such a non-Turing complete language? Well, he wouldn't be very impressed. Yet, it does support quite a lot of use cases, right? And its simplicity is very important for security as well. So if you have a simpler system, it's less vulnerable to potential threats. So what are potential Bitcoin script applications? For example, you can perform a proof of burn, which means you can, if you have a Bitcoin, so if I draw a Bitcoin transaction as such, with an input here and two outputs here, then you can make sure that this output here is not spendable, right? Basically, you cannot produce a Bitcoin script that would eval to true if you were to use that output. And this is equivalent to burning coins, right? So you can basically, that's a burning of a particular coin. You can no longer spend it. Then you can produce multi-signature addresses, which is quite important if you want to handle assets among multiple parties or for security purposes. You can pay for hash. You can do pay for hash pre-images. And there's you can use what's called lock time, which enables to perform micropayment channels, as we will see later in the scaling lecture. So there are a few applications that the simple yet interesting script already enables. And there are several projects that have tried to extend Bitcoin script to perform specific applications. One notable example is Namecoin, which we'll go into in a later module, in a later lecture. And so this allows you to, for example, to register a name. But there was prediction markets, decentralized markets in general, and financial instruments. So it's kind of the early stages of the Ethereum ecosystem or smart fully loop-enabled smart contract world, I think, that we have seen here on Bitcoin. But it was quite tricky to build such systems, so that's why more complicated smart contract languages then later evolved. Right, but these are the basics of Bitcoin and smart contracts. So you might ask, why not design a more flexible language? And this is what we'll be looking into the future lectures. Thank you very much for watching.